Zombie apocalypse.
So let's take a closer look based on ANSI AISC 360-10. So may nabanggit po dyan kasi chapter F or the design members for Flexural. So under F1 general provision, so this chapter provides the conceptualization to the members subjected to a simple bending about one principal axis of the cross section. So dinidiscuss lang nito yung mga chapter sections F1, F2 up until I think F5 or F6. So the important matter here is nagkaroon kasi ng development do sa mga the way we are going to design and investigate the sectional capacity of each section under design and allowable. Later, I will try to uncover so ano ba yung pinagkaiba ng design at saka ng allowable flexural strength. Which is very important sa pag-identify kung yung steel section ba is adequate to carry the load. Also, in the same section, dito nyo na magkakaroon ng idea, just like what I'm discussing before during plastic moment, the highest possible nominal flexural strength is the plastic moment, where the nominal moment equals the plastic moment. Very important yan. The question would be, in what particular case does Mn can be less than Mp? So, lahat ng mga bagay na yan ay didepende na sa pagiging compact niya or hindi. And as well as, is it slender? So, kung tatandaan natin, diniscuss natin in the past video lecture on how do we identify if the section is compact, non-compact, and slender. So, by that case, we will try to apply by imploring first, dapat marunong na tayo mag-compute ng check for compactness and followed by how do we check the flow chart kung anong type of compaction yung nangyari. So, ito yung magiging discussion natin for today. Knowing it is compact, knowing it is non-compact, knowing it is slender, how do we calculate yung mga titawag nating nominal moment capacity that we need to understand to say that if the section is safe or unsafe pagdating sa pagkarga ng load under consideration. Kaya naman siya dito, compactness depends on the flange and the web width to thickness ratios as defined in section B4 as well as meron din ito sa Nscp 2015. So kung makikita natin sa table na to, from being compact until it becomes slender, bumababa ang capacity natin, or what we call the nominal flexural strength. Bakit nominal moment ang unang kinukuha in this manner? Kasi tandaan natin, ang sectional property is already an inherent property. So we cannot say ultimate, we cannot say allowable to a particular sectional property since it is under at nominal condition. So, using the nominal condition, saka lang tayo magli-lead kung ano ang type of analysis na gagawin natin, kung ultimate ba under LRFD, or will it be at service state or what we call the WSD or ASD. So, dito nakikita natin yung relation ng normal strength at saka ng slenderness from compact until slender condition. Pero, tandaan natin na bawat beam, hindi lang yung section ng beam ang may kinalaman, pati yung mismong span ng beam, mahaba ba, maiksi, meron siyang function pa rin sa nominal flexural strength. And in accordance to the findings of ANSI AISC 360-10, ito naman yung relation. Same halos sila ng consideration. However, you will notice that ganun din, pababa ang kanilang nominal moment capacity from being supported until it reaches unsupported condition that we will try to discuss as we progress. So, hindi lang cross-sectional property ang may kinalaman, pati yung length of the beam. Kaya usually, we are being restricted on what particular length ang kaya natin i-apply sa mga steel. Usually, mahaba kumpara naman sa concrete design. Unless if you're using precise concrete design, that is different. We are talking about ordinary reinforced concrete design. So, alamin natin, ano ang participation, paano natin nako-compute yung nominal moment yan as a function of compactness. Siyempre, that's the main flow chart. Then finally, ano yung participation ng C sa B or in terms of the condition, that is what you call the coefficient of bending and so on, ano yung mga participating factor. Kasi dito, kung makikita sa table, from being plastic moment, pumunta ka sa 70% of the condition kasi ibig sabihin yan, 70% lang yung nare-retain sa strength . So, yung 30% is just a waste pagdating sa analysis until such value will reach the lowest possible strength based on the performance of the coefficient of bending as per the beam is considered, based on the lateral support na nagkakaroon. And usually, sa isang beam nga pala, no, by lay legends, makikita nyo may mga X mark. Okay? So, yung mga X mark na yan, that represents lateral support. So, sa mga plano, nakikita din natin yan. Okay? So, ibig sabihin niya, nagkakaroon ng konting support system sa direction yan. Either flange, ang ini-stiffen, automatic usually, web may stiffener pagkagaling sa AISC database, at saka sometimes, meron tayong tinatawag na plate stiffeners na nilalagay natin sa top and bottom flange or top and bottom flange and then connected in the web para at least magkaroon extra stiffener. Usually, wini-weld natin yan. Pero sa top flange naman yung kinakabit, yung top plate or bottom plate, nilalagay natin ng rivets. Or sometimes, pwede naman ding i-weld. So, those are the types of lateral support for a system of structure. So, the question would be again, how do we calculate those? This very important nominal moment capacity. Okay. Tingnan natin yung discussion ni National Structural Code of the Philippines 2015. So, under Section 506. So, pumapasin natin 506.1. Meron phi B times Mn that refers to design flexure. At tititawag natin LRFD. Okay? So, under new standards, tawag natin new LRFD. And there's what you call the allowable flexural strength as computed by Mn over omega sub B. So, therefore, ito naman yung nag-stand out for ASD, new. Bakit sinasabi ko na may new? Kasi before in Nscp 2001 and also Nscp 2010, meron kasing tinatawag na old ASD at saka old LRFD, especially Nscp 2000 or 2001, na kung saan iba yung pamamaraan ng pag-compute na tinatawag natin capacity of the steel section, na hindi ganito ang procedure. Until such time na nagkaroon ng bagong ng code, this is LRFD or load and resistance factor design, load resistance and factor design. So, nagkaroon ng konting revision sa mga code condition. So, kapag nakakuha na kayo ng nominal moment, to get LRFD, so MU, we need to get phi of bending times nominal moment, which is ang phi of bending laging 0.9 for LRFD. So, kukunin mo yung nominal moment. Now, for M, capacity, which is under ASD, which is Mn over omega B, which is, ang omega B natin is 1.67. So, usually, this is around 3 halves, I think. Rather, it's 4/3 as a function. No, 1.67, that's around, for a while, that's around, ano nga ba yung 1.67? Anyway, it's 5/3, I suppose. Yes, it's 5/3. So, this around the 5/3 of a constant. Okay? Now, may importanteng code provision na kinocompute si coefficient of bending C sub B. So, ang computation naman niya is 12.5 Mmax all over 2.5 Mmax plus 3 Ma plus 4 Mb plus 3 Mc times Rm. That is less than or equal to 3.0. Ibig sabihin, yung CB natin, hindi siya pwede lumaki sa 3.0. Otherwise, we will use 3.0. Pero ano ba yung mga nomenclature na yan? Ang Mmax represents absolute maximum moment. Ma is the first quarter, absolute moment. MB is the center line or the half of the unbraced segment. MC is the third quarter of the unbraced segment. And R sub n is what you call the cross-sectional monosymmetrical parameter. Okay. And 1.0 for doubly symmetric, ginagamit for R sub m, and 1.0 for singly symmetric members subjected to a single curvature of bending. Pero what if monosymmetric? Ibig sabihin yan, di ba? Kapag monosymmetric is what we call singly symmetric, sa isang side lang siya. So therefore, sinabi lang ng equation na ng paragraph na to is in singly symmetric members subjected to reverse curvature bending, kasi pwedeng single bending, okay, or reverse curve bending. Yan. Ito yung single, ito yung meron tinatawag na reverse. So, iba ang treatment. Ang tanong dyan, paano kino-compute yung sa RM ng reverse? Hindi na mention ng code ng Nscp 2015. So, how do we interpret that? Later, I will try to discuss paano kinocompute yung R sub M. Pero may mga conditions na ang CB is permitted conservatively taken as 1.0 for all cases. Pero ingat ha, itong code na to kasi ina-assume na ang gagamit na CB na-understand kung paano nagkakaroon ng load transfer tsaka moment transfer. Now, for cantilevers or overhangs where the free end is unbraced, the CB is 1.0. So, be careful to use CB kung kailan to nagiging non-1.0 at kailan siya 1.0. Itong user note is, anyway, you can compute naman itong mga values yan as you plug in the values. So, based naman sa version ni ANSI AISC 360-10, ganun din naman, yung MU, ginawa ng R sub U, no? Pag LRFD, you just multiply phi by R sub N. Ito yung MN, no? Katumbas nung sa kino-compute natin. Ito naman yung MU. Okay? So, yung phi of bending is the same, no? 0.9. Mamaya, makikita natin on this succeeding discussion. So, for allowable strength, so may subscript of A. So, parang pwede natin gawin na M na lang. So, pwede M sub A para ma-identify natin kung allowable o hindi. And then, this one is Mn over omega B. So, ito yung katumbas niya. Okay? So, gagamitin muna natin M sub A to represent the allowable capacity moment. So, ganun din na sinabi niya. Phi bending, 0.9 at omega B is 1.67 for AST. Same na same sila. So, ganun din naman si C sa B. Sinabi niya ganito. Okay? So, ganun ulit. Mmax, 3MA, 4MB, MC. So, discuss lang natin ng konti. Assuming that we have this beam, pag wala kayong nakitang cross, ibig sabihin yan, yung mismong span, or kahit walang cross ang span, siya yung brace length, L sa B. Okay? So, ibig sabihin, you have to divide this into 4. Okay? So, L over 4, L over 4, L over 4, L over 4. So, ito yung A, ito yung B, ito yung C. So, kukuha kayo ng mga moments on each portion. So, dito makakuha si MA, si MB, at si MC. And to note, kunin nyo yung absolute. At ito yung moment diagram kasi yung Mmax should be also absolute, free from negative sign. Okay? Pero what if hindi naman dulo-dulo yung brace length? For example, you have this beam. Sample lang po ito. So, basta't may makita kayo X, automatic. Ayan. Okay? So, automatic yung hinge at roller, kahit walang lagyan na X, X lang yan. Pero sabihin na natin L1, L2. Your next objective is to get the largest brace length. So, L1 and L2 ang givens. Okay? So, if L2 is more than L1, then yung L2 ang magiging brace length, yung pinakamalaking brace condition o yung na-stiffen. So, out of that, then dyan ka magdi-divide ng 4. So, this will become L2 over 4. Mali lang yung aking nomenclature. So, by the way, that should be like this. Okay. This should be L sub 2 over 4, L sub 2 over 4, L sub 2 over 4, and L sub 2 over 4. So, ito na naman si A, si B, at si C. So, dyan ka kukuha ng mga moments sa A, sa B, and C. Question, saan mo kukunin si maximum moment? Tandaan po ninyo, sinasabi na naman dito, absolute value of maximum moment in the unbraced segment din. Ibig sabihin, dito ka din kukuha ng maximum moment somewhere there. So, kung saan nagkakaroon ng peak point, yung value, saan siya maximum sa negative or positive, basta i-take the absolute, that would be our maximum moment. So, pinakamaganda dito, i-drawing nyo yung moment diagram. And ginagawa ang CBS 1.0 if and only for cantilevers or overhangs where the free end is unbraced. Also, may tinatawag na insignificant symmetric members. Ito yung sinasabi natin kanina, To reverse curvature bending, the lateral torsional backing strength shall be checked for both flanges. The available flexural strength shall be greater than or equal to the maximum required moment causing compression within the flange under consideration. But the question would be, paano kino-compute yun? Yan yung R sub N relation na sinabi naman ni AISC 360-10 kung paano. But before we move on to that, meron kasing historical development yung C sub B. Now, ito yung sinasabi ni Nscp 2000. Okay? Kung makakuha kayo ng document, ito yung kino-compute natin noon to get the C sub B, where M1 and M2 is a smaller and larger moment at the end of the advice link. Very popular ito noon, lalo na nung kapanahunan na NECP 2001. And usually, nagiging totoo lang daw yan based on this manuscript from ANSI AISC 360-10 is only applicable for moment that consists of straight lines between brace points. Ibig sabihin, concentrated yung mga load mo. At syempre, pag nag-drawing ka ng moment diagram, baka ano yan, linear or first degree. However, syempre, may 0 degree load ka. Also, sometimes, di ba, it is realistic to consider second degree, hindi yung first degree kasi lalo na sa mga tinatawag nating overhang. Usually, ang load talaga niyan second degree. So, therefore, magkakaroon ng issue. So, which is a condition that is rare in beam design kasi nga may beam weight, no? 0 degree load. So, pag drawing mo yung parabolic, performance of parabolic equation. So, therefore, there should be a realignment of that. Kaya ito nag-arrive sa C sub B equals 12.5 Mmax all over 2.5 Mmax plus 3Ma plus 4Mb plus 3Mc, where all moments are considered absolute. Ngayon, dahil nagkaroon ng epekto si lateral torsional buckling as explained here, so naging ganito yung equation. Nagkaroon ka ng times R sub M. O yung tinatawag nating function nito para do sa monosymmetric condition. Ngayon, if single curvature in bending, regardless of being fixed support or whatsoever type of beam like that, R sub M is always equal to 1.0. However, if you have a reverse curvature bending, ibig sabihin nung una, ang beam bending natin pwedeng bumaba or pwede naman tumaas yung deflection. Okay? Or kahit continuous pa yan eh. Okay? So, basta na-understand nyo lang kung paano mag-bend. So, lahat nila is single curvature. Pag sinabi nating reverse, is nagkakaroon ng parang malakilay na bending. Already proven by theory of structures. Eh. So, how do we compute that? That is just only 0.5 plus twice of the IY top over I sub Y raised to 2. So, paano kino-compute yan? Let's say, for example, you have this I shape. Ang instruction to get that is I sub Y, no? So, if this is the X and this is the Y, sinabi ng IY, no, simulan natin sa I sub Y, moment of the inertia of the intersection about an axis through the web. So, padadaanin sa web, kukunin mo yung weaker inertia on the whole. And then finally, the moment of inertia of the top flange about an axis through the web. So, yung top flange lang yung kukunin. At ito yung kukuhanan mo ng inertia. So, IY. So, meron kang IY top na kukunin. At i-divide mo siya sa buong I sub Y no section. And then raised to 2 times 2 plus 0.5. So, ito lang yung computation ngayon sa R sub M. That was not mentioned in our NECP 2015. Okay, ngayon, what if the section is compact? No, syempre, there's a need to check first, no, if compact, non-compact, or slender. What if compact sections, or pag sinabi natin compact section, should be both web and flange ang compact. So, both should be satisfied. So, ano sinasabi ni NECP 2015? So, here are the procedures. But before that, is mentioned on 506.2, maraming case kasi yan. Ngayon, for doubly symmetric compact I-shaped members and channels bent about their major axis, ibig sabihin yan, dapat na-satisfy mo muna yung pagiging doubly symmetric, which is all W-shaped section in the database are doubly symmetric, at tsaka on the major axis. So, ibig sabihin, ang load natin, nagtatranscribe dun sa moment of inertia along the stronger axis, or patayo ang I-beam mo, tapos gravity loads ang nilagay mo. So, therefore, ano ang selection ng M sub N? So, the nominal flexures to M sub N shall be the lower value obtained according to the limit states of yielding and lateral torsion buckling. Dalawa ang pagkukonsiderahan natin. Yielding condition at saka lateral torsion buckling. So, check natin kung paano kinocompute natin yung dalawang yan. So, sa yielding, 506.2.1, very popular na sa atin ito na nagagamit natin before in the past video lecture. So, Mn is equal to Mp equals Fy Zx. So, tandaan po natin, yung pinakamaliit po ang pipili natin as mentioned here, the lower. So, alam na natin kung paano kinocompute ito. At saka usually, kapag may AISC database ka naman, you just get this table. you just get this value on that particular table. So, medyo madali na. Yung FY, titingnan mo na lang anong steel gauge yung ginagamit. Already discussed in my past video lecture, ano yung mga available values sa FY at FU, depende kung anong ASTM specs yung gagamitin. Ngayon, for lateral torsional backlink, 506.2.2, may tatlong criterion. If LB is less than LP or equal to that, you don't need to compute the lateral torsional backlink. Pero kapag nasa pagitan ka ng LP, LB, at L sub R, so you need to compute this equation. So, madali naman. Kaya may participation yung C sub B natin. Pero if your LB is more than L sub R, then the nominal moment should be the critical stress times the sectional modulus as X. But kung mapapasin nyo, hindi dapat sila tumaas. Sabi nga ng code natin, pinakamataas kasi plastic moment. Already discussed before, bakit yan ang pinakamataas? Due to the fact that we already proven many times before that the plastic moment should be always the maximum value that the steel beam can carry, that the steel beam should be under that capacity. Kasi otherwise, failure will happen. Ngayon, how do we compute? No? Ang LB is the brace length. Diniscuss ko na kanina. The length between points that are braced against lateral displacement of compression flange or braced against width of the cross-sectional area. And to get the cross-section, the critical stress, you have to compute this. So, yung value na R sub TS, okay, nasa table din naman. So, you can now use that. Yung J, nasa table. H sub O, nasa table. S sub X, nasa table. So, yung C, mayroon code tayo dyan. Tsaka yung E, ano? Constant tayo sa 200 gigapascal. So, paano ba computein yung LP tsaka LR? Sa LP, kapag both sections are compact, you have to compute this. LP is 1.76 times RY square root of E all over, o E over FY. So, yung R sub Y, nasa table naman natin yan. So, tinuro ko naman sa inyo, pag walang available table, makocompute at makocompute nyo yan. Pero pag pinagagamit naman yung table, then use all of those values. L sub R. So, may makocompute ka din naman. No? Yung nga lang, medyo mukhang mahaba. So, ang kakaiba dito, ano yung value ng C? So, ang value ng C, kapag doubly symmetric, no, is just only take is as 1. Pero pag channel, which is hindi natin scope for today's discussion, then that is H sub that all over 2 quantity AY over CW. So, don't forget to consider this. And then, diniscuss ko na dati ito, yung RTS squared equals square root of IY CW over S sub X. If you have the table, you just use the table. A sub O, already defined before, the distance between the flange centroids. Okay, but may user note. Actually, mga simplifications na lang ito, kahit hindi nyo natingnan, pero dahil meron ka naman equation na nasa kaliwa, you can use already. So, ito lang naman yung mga simplification condition. So, hindi ko na i-focus yung discussion nito kasi madiderive naman ito eventually. So, sa version naman ni ANSI AISC 36-10, ulitin natin, ito yung naging mother code ni Nscp 2015. Ito yung pinanggalingan ng lahat ng code natin sa Nscp Chapter 5 of Code 2015. First printing and or second printing yan. So, kung maalala ninyo, ito naman si F sub 2, doubly symmetric compact I-shaped members and channels bent about their major axis. So, same pa rin sila. Ang maganda dito, sinabi rin niya. So, ito, na-prove naman, at na-discuss naman natin ito before, checking for compactness. So, mapoprove naman kung bakit ito naging mga non-compact under 345 megapascal only. And so on. So, anyway, if you just only guided with the table, then madali naman ma-identify. And ganoon din yung sinabi, ano, the nominal flexural strength Mn, ito yung interest natin, shall be the lower value obtained according to the limit states and lateral torsion backing. So, dalawa ang pinagpipilian. Okay, dalawa. Ito yung una, ito yung pangalawa. So, ganun under yielding, ganun pa rin computation natin. So, yung titawag nating yield strength, no? Kung maalala natin, ito yung condition for the plastic moment, Fyzx. So, yield strength naman natin, just only Fysx, no? So, function siya na equation sa in the checking of compact and non-compact, okay? So, ganun din naman si lateral torsional backing, same equation. So, A, B, and C, same lang din naman pinapakita nila ng Nscp. And, same computation F sub CR. So, C naman is ganun pa rin. I-discuss natin later. So, ganun pa rin computation na nakita natin. Si LP, si L sub R, wala pinagkaiba. RTS squared, pero kung may table, pwedeng kunin na lang doon. And C is equal to 1 for doubly symmetric. So, ibig sabihin, lahat ng nasa database natin ng W shape, M shape, S shape is already C of 1. Pero pag channels, okay, C, MC, so you have to use this equation. Pero that, again, is discussed on a separate discussion. So, ganun din, yung niloloob nito sa Nscp 2015. User note lang yan. You can derive this anyway. Pagsamahin nyo na yung C sub W at saka yung RTS. So, you can derive this anyway. Tsaka the same with this. Assuming a 1/6 of the web compression. So, madali ito ma-derive. So, pero what if naman kung section natin is compact ang web, pero non-compact naman or slender yung flange? So, focus natin yung main problem ng beam natin, no? So, ibig sabihin, this is already a non-compact section. But, non-compact lang siya pagdating sa flange. Okay, pero talk about non-compact pa rin in intersection natin. Ibig sabihin nito, yung BF over 2TF natin, okay, is naging more than okay, oops, more than you need to erase this. Saan ba yan? Okay. Okay. Nag-more than siya sa lambda P or nag-more than siya sa lambda R. Yun lang naman yung ibig sabihin yan. So, wala siyang pakialam kung ano yung condition ng flange, either non-compact or slender. Basta, compact lang yung web. Sabihin ng compact yung web, na-achieve natin yung H over TW, na H is equal to T. So, yung T, kakaroon na ano yan, no? Difference sila, ulitin lang natin. Yung H, yan yung walang stiffener, at yung T, may stiffener sa web. Pero same pa rin sila ang sinatawag na H. So, therefore, para maging compact yan, dapat less than sa condition ng lambda P for under the flange. Okay? So, to continue, tingnan natin sinasabi ni Nscp. So, under doubly symmetric na I-shaped members with compact waves and non-compact or slender flange, again, on major axis muna. So, focusan na natin. Yung nominal moment shall be the lower value of the following. Lateral, torsional buckling, number 1, and compression flange local buckling, number 2. So, dalawa. So, yung unang state, ito yung 506.3.1, pero may pinagkaiba na sila nung una. Okay, kung mapapasin nyo, yung kaninang code is the same lang din daw ang computation sa nauna. Pero sa compression flange local buckling, nagkaroon ng modification. So therefore, this will be the computation. Okay? So medyo nagkaiba na. Pero tingnan nyo application. Kailangan for section with non-compact, ito yung kukumpitin. Pero pag section man is for the flange na nag-slender, ito yung gagamitin. So this cannot be used both. No? Tingnan natin kung saan siya naging condition. No? Non-compact ba or slender yung flange. So, yung lambda P sub F, lambda R sub F, okay, are still the same with the table. Binago lang yung subscript, pero same lang din sila ng pinanggagalingan. The limiting slenderness, na based sa table na present ko on the past video lecture. And then the case sub C should be for all over H over TW and shall not be taken less than 0.35 nor greater than 0.76 for calculation purposes. Ibig sabihin yan, yung case natin, napapagitnaan siya ng 0.35 at saka ng 0.76. Ibig sabihin, pag bumaba ka sa 0.35, then if KC is less than 0.35, then automatic na yung KC natin, no? Automatic 0.35. So therefore, if KC naman natin is nag more than 0.76, then your KC should be 0.76. Kasi that's the paragraph says, ano, shall not be taken less than. Okay? Now, based on ANSI ASC 360-10 of the same particular topic, so ganun din, no? Yung nominal moment should be the lower of the value from lateral torsional buckling at saka compression plus local buckling. So, 1, 2, dalawa yung pagpipilian. Now, for lateral torsional buckling, same provision nung kanina, doon sa nauna, yung compact sections. And for compression flange local backlink, ganun din yung pinapakita, no, yung lambda PF, lambda R sub F. So, for compact flange, for slender flange, ito naman. So, ganun din yung ganyang, nagkaroon ng transcription dito. Highly similar. Ngayon, what if non-compact web? Okay? So, sabi ng Nscp 506.4, other I-shaped members with compact or non-compact webs. Sabihin, wala na siyang pakialam kung ano nangyari sa flange mo, basta yung web pa lang is nagkaroon ng conditions na to. So, kailan nag-a-apply yan? Basahin natin. So, the section applies to, una, doubly symmetric I-shaped members bent about their major axis with non-compact webs. Ibig sabihin, wala na siyang pakialam kung ano nangyari sa flange mo, no? So, basta yung web mo naging non-compact agad. Also, in a singly symmetric I-shape, so alam na natin kung ibig sabihin ng singly symmetric. So, one-sided symmetry or monosymmetric ang tawag. That is the members with webs attached to the mid-width of the flange. Ibig sabihin, nagkakaroon ng special attachment and then bent about their major axis with compact or non-compact webs. It's either one of the two. Ngayon, how do we select the nominal moment? Okay? Shall be the lowest among the two, among these following. Compression flange, yielding, number 1. Lateral torsion backlink, that would be number 2. Okay? Lagyan natin dito ng 2. Compression flange local backlink, number 3. And tension flange yielding, number 4. Apat, yung pagpipilian natin, and then whatever gives the lowest should be the value. Pero there's a user note, no? I-shaped members for which the section is applicable may be designed conservatively using section 506.5. Yan yung susunod na code natin. Pero, let's stick with this muna. Tingnan natin kung ano yung dapat na flowcharting. Now, for compression flange shielding, so ito yung number 1 criterion. So, RPC, MYC, also equal to RPC FY SX. Kasi ang MY sub C is FY S sub X. So parang yielding condition siya. And RPC refers to web plastification factor. At yung SXT, SXC is an elastic section modulus referred to tension and compression flange respectively. So mamaya i-demonstrate ko paano kino-compute yan. Okay, for number 2 criterion, the lateral torsional backlink in accordance to 506.4.2. So, pagpipilian natin yung LB, LP, tsaka LR ulit. So, may pagpipilian ulit, ano? So, tingnan natin kung saan mag-fall under, then follow this flowchart. So, sinabi naman dito ng kompleto kung paano kino-compute yung mga nominal moment capacity. Okay? So, may mga aspect ratios tayong titingnan. For IYC over IY that is less or equal to 0.23, then J shall be taken as 0. Tandaan po ninyo. So, bago nyo lagyan ng value yung J, ito, related siya dito. Okay? So, J will be 0. So, therefore, square root of 1 na lang ito mangyayari. Pero, kapag nag-more than 0.23, then J should be taken from the table or from the computation that I have already discussed before. So, IYC and IY, yung katulad ng diniscuss natin kanina. So, hanapin nyo lang yung compression. IYC is referring to the weaker inertia of the compression flange. Okay? The stress F sub L. Kasi sa equation natin, may pangailangan sa F sub L if this condition number 2 prevails. So, ito yung computation. Ganun ulit. So, dependent sila sa X sub C, X sub XT, X sub XC. So, may mga conditions yung FL nila. Okay? So, LP, ito kino-compute siya ngayon. So, medyo nagkaiba sila noong una pag compact sections, tsaka LR, no, medyo magkaiba. Again, yung J na to, dependent, ano, kung ano makukuha nating relation IYC over IY. So, RPC, web classification factor, kung naalala niyo, very important din siya. So, ito yung way of computation, may A and B ka. So, lambda PW, just only lambda P sa table na pinakita natin before. At you have to follow this system of linear inequalities. So, para masunod natin, ano yung totoong susunod na RPC. So, determine nyo muna kung A or B. Mamimili tayo based on the classification kung saan napupunta. Yan ba yung nag-less than equal sa lambda PW or baka nag-more than sa lambda PW. If less than equal, ito yung kukumpitin. Okay? If more than, then this should be the computed value. So again, ulitin natin, ang MP is just only ZX, FY, ganun X sub XC, tsaka X sub XT, so same as with the lambda, lambda PW, and then lambda RW, where lambda is to be checked as HC over TW. Yung H sub C, diniscuss ko na before. Minimeasure yan sa ilalim ng top flange, kung compression yung top, until the neutral axis. So, si effective radius of gyration. Kanina, sa compact section, ang RTS ang ating effective radius of gyration. Pero kapag naging non-compact web, R sub T na lang yung tawag. So, for I-shape with rectangular compression flange, ito yung gagamitin natin. Okay, so very clear naman na sinabi kung paano ginagamit yan. At saka may user note naman, you can read this. Actually, itong code na to, ito yung ginagamit ng Nscp 2001 para ma-compute yung effective radius of gyration R sub T. Yung may 1/3 of the compression portion of the web. So, hindi pa rin kinakalimutan ni Nscp 2015 and or ASC 360-10 yung effective radius of gyration under such condition. So, yung number 2, ganun din naman. For I-shape channel caps or cover plates, so iba na yung approach niyan. Okay, yung third criteria naman, this is under 506.4.3, compression flange local backlink. So, you can get these equations then. No? So, number 1, for sections with compact flanges, the limit state of the local backlink does not apply. Pero kapag non-compact naman yung flange at saka slender yung flange, so you have to follow this. So, nagkaroon ng web classification factor. So, medyo na-modify na konti. Tsaka F sub L. Okay? So, medyo madali naman siya sundan. Ito yung fourth criterion. So, tension flange shielding. 506.4.4. So, X sub XC, tsaka X sub XC naman ang kino-compare. So, just following this condition by computing H sub C over TW, ito yung mga criterions niyan, and then you can get the R sub PT, where R sub PT is the tension flange shielding limit state. Okay? The web classification factor for such. And then again, this is the nomenclatures used. Very easy naman to understand. Now, in equivalence to AISC and C360-10, so ganun din yung sinasabi niya. So, nominal moment capacity should be the lowest among these, no? First state is the compression flange shielding, number 1. So, ito yung number 1 natin. Lateral torsion backlink, number 2. And compression flange local backlink, 3. And also, tension flange of yielding is number 4. So, ganun din ulit, no? Sinabi nung number 1 criterion. So, sa PC, yung classification factor sa web, under compression yan, where MYC is the yield moment in the compression flange in kipinch or Newton millimeter. So, paano ba kinocompute yung X sub XC at X sub XC? So, sinasabi lang ni ASCII 360-10, ngito kinocompute. Si X sub XC is kinocompute yung IX over Y, while X sub XC is IX over D minus Y. Ibig sabihin yan, kinukonsider yung top and bottom condition. Assuming compression and tension yung location ng top and bottom respectively, then dito natin mailolocate yung direction ng S sub XC at ito naman yung direction ng X sub X under tension. So, sinaseparate lang niya, in short. So, ganun din sa MYC. So, para nagkakaroon ka lang ng yield condition, tsaka under tension and compression respectively. So, ito yung number 2 criterion. So, highly similar sila nung nauna na under from the Nscp 2015. So, ganun din yung commentary to compute LP and LR. So, same sila nung nasa Nscp 2015. So, web classification factor R sa PC, ganun din yung way of computation. So, notice, no, highly similar sila ng mga relation kasi ang Nscp 2015, ulitin lang natin, inadapt yan from ANSI ASC 360-10. So, andito yung mga nomenclatures niya. Easy naman to understand. So, ganun din. Yung computation R sub T, yung effective radius of gyration. Sa compact web, matawag sa kanya R sub TS. Pero dito, R sub T na lang. So, ito yung number 3 criterion based on compression flange local backlink. So, dinescribe naman yan na maayos kung paano natin kino-compute yan. Also, number 4, the last criterion for non-compact web. So, clearly stated naman kung paano i-compute based on this, if A or B or C yung nag-satisfy. Or A or B, I mean. Ngayon, punta natin, what if slender section na nangyari? So, according to Nscp 2015, 506.5, doubly symmetric and singly symmetric, or what we call monosymmetric, yung singly symmetric I-shaped members with slender webs bent about their major axis. Ngayon, sabi dito, this section applies to doubly symmetric and singly symmetric I-shape with slender webs. Slender na yung web. Kasi pag slender web, wala nang problema sa flange eh. Kasi automatic, nadadami niyo sa galawan ng web. Tandaan niyo. So, pag ang web, ang nagkaroon ng konting galaw, so yung flange mo, gumagalaw na rin yan. So, ibig sabihin, originally, nandito yan. So, bumaba. Okay, nagkaroon ng movement. So, yung web na yung mismong problematic. So, how do we compute the nominal moment? Shall be the lowest of the following. Compression flange yielding, that's the criteria number 1. Lateral torsion backlink, criteria number 2. Compression flange local backlink, criteria number 3. And tension flange yielding, criteria number 4. So, criteria number 1, compression flange yielding, ganun ulit. But, yun nga, nagbago lang, R sub PG na ngayon. Okay? 506.5.1. Okay, ito naman yung next criterion, which is lateral torsional backlink. So, R sub PG, okay? So, 506.5.2, ganun ulit. Diniscuss yung LBLP, comparison level. And the way we compute LP is the same as 506.4-7. And LR, ito na, no, pi RT square root of E over 0.7 Fy. Then si RPG, that's what we call the bending strength reduction factor. So, this is the way we'll calculate that. Less than or equal to 1.0. Ibig sabihin yan, if your R sub PG is more than 1, then use RPG equals 1.0. So, A sub W in RT is diniscuss naman in accordance to this. But should not exceed to 10 yung A sub W, sabihin A sub W less than equal to 10. Otherwise, 10 yung gagamitin pag nag-more than. Effective radius of gyration R sub T is already discussed in the previous code, no? Dito sa video lecture na ito. Another criteria for compression flange shielding, okay, ganun ulit. So, may computation na naman ulit na gagawin dyan. And then, tingnan natin kung saan siya nag-apply. So, you have to check carefully itong 3 criteria sa to. Okay? So, KC, lambda, lambda P, lambda RF is already measured on how to deal with that. So, tension flange shielding, so ganun ulit, i-compare yung X sub XT tsaka X sub XC, depende kung saan maglalagay, no? Kapag more than equal, does not apply. Pero pag less than S sub XC, then MN is equal to FYX XT. Okay, so ano yung katumbas siya sa ANSI ASC 360-10? So, same lang sila na kinonsider. Nominal moment shall be the lowest value obtained according to the basis of compression flange shielding, number 1 criterion, lateral torsion backlink, number 2 criterion, compression flange local backlink, the 3rd criterion, and tension flange shielding, the 4th criterion. So, compression flange shielding, same sila ng Nscp 2015. So, ganun din si second criterion. So, clearly stated, talaga similar sila. So, kompleto yung pagkaka-adapt ni Nscp sa kanya. Tandaan nyo, may mga sinasabing mga equation dito. So, balikan nyo lang yung mga previous code kanina. Madali naman makita. Third criterion, ganun ulit. Okay? And the last criterion, so same sila ng Nscp 2015. So, tandaan natin, yung mga una kong code na sinabi, bent about the major axis. What about kung nasa minor axis yung bending? Just like an I shape, okay, na nagkaroon ng lateral. So, nagkaroon ng sideway bending. So, minor axis ang kanyang bending. So, papaganon siya. Literal, no? So, yung pati top and bottom flange mo, may epekto yan. So, how do we deal with that? So, for Nscp 2015, tandaan natin, puro I-shape lang muna kasi may ibang code naman yan sa iba. So, 506.6. So, the nominal moment shall be lower value obtained according to the limit states of yielding and flange local buckling. So, una, for yielding, Mn is equal to Mp, Fyzy less than equal 1.6 of Fysy. So, therefore, if Fyzy becomes more than 1.6 of Fysy, then your Mn is simply 1.6 Fysy. Kasi dito, pag nasunod mo to, ito yung value ng MP mo eh. MN mo, MP. Okay? Which is Fyzy. According to the weaker dimension. And for launch local backlink, so as mentioned completely, nandito naman kung paano siya kukumpitin. So, ano siya, well mentioned. So, sa sinasabi naman ni T60-10, same lang sila. So, dalawa yung criterion. Okay? First criterion and second criterion will be on the next slide. Ayan. Yun nga lang, may sinabi lang dito si NISC, ANSI, AISC, TCC-10, I-ship members and channels bent about their minor do not experience lateral torsional buckling or wave buckling. Yung explanation ba't hindi kinukuha yung L sub LTB na tinatawag or lateral torsion buckling condition. The only limit states to consider are yielding and flange local buckling. So, din-explain niya. So, the user note informs the designer of the few rolled shapes that need to be checked for the flange local buckling. So, critical tayo sa flange local buckling. Ganun din. Yung sa second criteria kung paano kinocompute. Transcribing all this information. Ilalagay nyo lang doon sa values na yan. Okay, so thanks for viewing. This video lecture is intended only for I-shape. So if you want to see paano naman sa HSS, round SS, RSS, I mean angle, single angle, double angle, I will make a separate video lecture out of that. So that will be to be presented in one of my video lecture. For the meantime, dito muna tayo mag-focus sa I-shape and then on our next video lecture, we will try to apply those conditions. So I hope that you learned something new today. And again, as our tradition goes, you have been neurorized and see you in our next video lecture.